Welcome everyone to Hudson and Thames' very own reading group. And in this reading group today, the model that we'll be exploring is called Beyond the Black Box, which provides us with an intuitive approach to our investment predictions using machine learning models. And this specific paper is from the Journal of Financial Data Science, and Michelle Andrews, I will take us through this paper today. I am a quantitative researcher at Hudson and Thames, and I also have an MCOM in advanced data analytics. So what I'll do today is I will explain why this model Fingerprint, which is another name for this model, is how it tries to overcome this black box phenomena, what makes it unique, and then I'll try to show you that it's basically just an adaptation of some of the feature importance methods that we already know, and certain models were selected for this paper, so I'll try to explain why and just give a brief summary of each. And then I will split the model Fingerprint into two parts. So the first part will just be how do we actually calculate specific effects for predictors, right? Because this is in essence the foundation of this model. So we have a linear effect, we have a nonlinear effect, and if we're looking at two predictors together, we have a pairwise interaction effect. And then lastly, the paper gives a currency market example, and this is what we will use to decompose performance. So we'll use this model Fingerprint summary across different models to compare these models, and we'll just see like why the model Fingerprint is so effective. So how do we actually overcome this black box phenomena using this model? So we know that it's important, right? The more we increase the complexity of our machine learning model. So for example, if we have an ensemble method we're trying to apply, the more models we add, the more complexity increases and the more difficult it becomes to actually interpret what this huge model is doing. So this is a barrier for especially investors in the finance industry, because if something goes wrong, how can you go back to the model and really understand why certain predictors were chosen if it's so complex that you can't even interpret why your model chose these predictors in the first place. So this is what the model Fingerprint tries to remedy. So it just quantifies the influence of a specific predictor, and this helps us to compare across different models, right? To see, well, what influence does this predictor really have on our predictions? And we can also more accurately interpret our results if we actually know the specific effect that a predictor has. And as I said, these effects can be linear, they can be nonlinear, and it can even have a pairwise interaction effect with another variable. And this is what point 3 is trying to establish, is that we can actually better understand relationships between our predictors once we can calculate this pairwise interaction effect. And then as a fourth point, so this paper explores a financial industry type of application, but wherever there exists a feature selection problem, this model can be applied, which is great. And the models chosen for this specific paper can be applied to both a regression task and a classification task, which makes this model very, very versatile. So within the realm of perturbation techniques, right, we find this model Fingerprints. As I said before, it's just an adaptation of some of the feature importance techniques we already know. And if I can quote Professor Marcos Lopez de Prado, he said that, backtesting is not a research tool, but feature importance is. So it's really important to understand why a model assigns a certain weight to a predictor, right? And then what is the influence of that predictor on your predictions? So feature importance techniques that we're already familiar with, things like MDI, MDA, SFI, shapely values, and the line algorithm. So some of these methods are model specific. So for example, this first one over here, MDI, so we can only use this model in random forests. So unfortunately, this limits us in comparing our feature importance technique across different models, even though this method is computationally cheap. And then your MDA, which is mean decreased accuracy, even though it's model agnostic, which is great, so we can compare across different models. The moment you have correlated variables, something called substitution effects can take place. So one correlated variable might contribute the same type of influence on the predictions as another correlated variable, but this MDA technique will not assign the same weight, for example, to each of these features, even though we know that this is true. So that's a downfall of this method. And then for your single feature importance, so this method is very intuitive because we sequentially calculate the effect of each of the predictors, but unfortunately, because of the way that this this single feature importance method works, it's just extremely computationally expensive. So the Shapley values and the Lime algorithm, so these are the last two I just quickly want to mention. So they're great in the sense that they are model agnostic, but unfortunately Shapley values have the same issue of being computationally expensive, and then the Lime algorithm is dependent on setting your hyperparameters. So these hyperparameters are very sensitive. If they are not set correctly, they can have large effects on your feature importance results. So this is one downside of the Lime algorithm. And what makes this model Fingerprint unique is not only is it model agnostic, which is great, but really provides you with a summary that you can lean on the moment your model either makes great predictions or very accurate predictions, or when your model performs poorly. So you have something to fall back on. And then also, because it calculates a pairwise interaction effect between specific predictors, you don't have that adverse effects if substitution effects correlated predictors are present in your model. So yeah, that's what makes the model Fingerprint so unique. And the reason these specific models were chosen for this paper is firstly because each of these models can become increasingly complex, right? And we'll see that later on in the paper as well, how we can compare across these different models. But also each of these models can be used to either perform a regression task or a classification task. So this will also just show what makes this model Fingerprint so nice to use. So a random forest, just briefly, it consists of many different decision trees. The more trees you add, the more complex it becomes. And these trees just have to break down your predictors into many different decisions, which will ultimately make a prediction for a specific observation. And we can cast sort of a majority vote across our decision trees within our forest, and this will help us to get a prediction for an observation. And a gradient boosting machine. So as the name says, we apply this type of boosting intuition. So we take predictors that are weak predictors in the sense that they don't make accurate predictions, and then we try to boost them to be strong predictors that generate accurate predictions for our model. And how we do this, and this again is why this model can become very complex, is we iteratively add not only data, but also mistakes that were made from one iteration to the next. And we do this by minimizing the loss function. So we train our predictors every time we decrease this loss function, and we do that with a gradient descent-like procedure. And gradient boosting machines, so they're not the only method. So there's also ADA boost and XG boost. So yeah, just to take note of that. And a neural network. So again, we know how this can become increasingly complex if we have all of these nested layers, right, with nodes that have to assign weights. What's great is that we can identify complex relationships, but on the downside, yes, we don't know, why this model assigns certain weights to specific predictors. So a neural network, in essence, is just taking in unstructured data, so extremely complex inputs, and then identifying specific relationships and then making a prediction. Okay, so that's just a broad overview of the models chosen. And what we can do now is we can break our model Fingerprint down into its effects and how it can be applied to models. Okay, so what we need to look at is a partial dependency function, and this is what we'll use to decompose your predictors' effects into either linear or nonlinear, and we will come back to this function so that I can show you guys how you can actually use it to also calculate pairwise interaction effects between more than one predictor. Okay, so essentially what we're trying to do is we're trying to establish, well, what is the marginal impact of a specific predictor on predictions? So what we can do and what we normally do is we have a model that we choose, so random forest, gradient boosting machine, or a neural network, and we have specific predictors that we are going to use to make a prediction. So we have turbulence in the market, spot return, and valuation, and we're going to use these three, for example, to calculate what's going to happen to the currency market. Okay, and then we get predictions. So what we're going to do instead to get a marginal impact of a specific predictor is we can, for example, isolate turbulence. And according to a specific technique of your choosing, you can vary the values of turbulence iteratively. And each time you do so, you will gain a new set of predictions called partial predictions. And as I showed here, every single time you vary the values of a specific predictor, you will keep the values of the other predictors fixed. And this is how you obtain the marginal impact of a specific predictor. And the intuition behind this is if you vary a specific predictor and each time obtain different predictions, you will be able to see the fluctuations in those predictions, right? Are they large fluctuations or are there no fluctuations at all? If there are large fluctuations, then we can safely say that, for example, turbulence is a highly influential predictor. Whereas if there are no fluctuations, if the predictions remain the same, every single time you vary this variable, then you can say, well, it really doesn't have that much of an impact on our predictions. And as I said here in this last step, so you can just apply this logic to each of your predictors. And this is how you will gain the marginal impact of both turbulence, spot return, and then lastly, the valuation. Okay, and again, as I said, we are going to decompose this partial dependence function into a linear effect and non-linear effect. And then we will come back to this partial dependence function and I'll show you how you can decompose it into a pairwise interaction effect as well for more than one variable. So as I said, this is basically what we're going to do now. And I'm going to start with the linear effect, then I'll show you the non-linear effect and then the pairwise interaction effects. Okay, so for our linear effect, the formula over here, just so that you can follow along in the paper. And then we also see that within this formula, we have a deviation. So I'll show you guys in this graph here to the right, why we need to understand, the intuition behind this deviation. But firstly, if we think about a linear effect, a specific predictor, so as we can see here in the graph, let's say turbulence. So this predictor can have a linear effect on, let's say, the currency, as we saw before. So they can move together, right, linearly. So, for example, if turbulence increases, the currency market rate will also increase. Or it can have a negative linear effect. So if turbulence, for example, increases, the currency market will decrease. So that can, or the currency market rate will decrease. So we just need to keep that in mind. And then we also said in the very beginning that we can quantify this influence. In other words, if this deviation is very small, then we might not really have a linear effect at all. So we can have no linear effect. But we can also see that as this deviation increases, we can either have a moderate linear effect for a specific predictor, and we can also have a very strong linear effect for a predictor. So this is what this graph is essentially trying to say. And we can see that we have our linear fit, and this is the red curve over here. So that's the first part of the deviation. And then we have an average, right, of our partial predictions. And that's the this black curve over here. So it's the deviation between these two things that determine the linear effect of a predictor. And I broke it down over here just to show you essentially what happens is we use our original predictor. So let's say turbulence as is, and we are trying to see, well, what is the linear relationship between our original predictor and the predictions it made, right, when we varied it over iterations. And then if we obtain these predictions, we can just remove the average, right, to be left with the effect, the linear effect that this specific predictor has on the currency market. So we take the absolute value of these deviations, and then we take the average, and this gives us the linear effect. What I can then also show you for the nonlinear effect is firstly that we have more or less the same function. So the only difference is that we, in the nonlinear effect, we use the partial prediction as is, whereas in the linear effect, we use the average. So again, we can see that we are measuring a deviation, and we can see in the curve here to the right, for a specific predictor, we can have no nonlinear effect over here, and over here. Or we can have a moderate nonlinear effect, or we can have a strong nonlinear effect for a specific predictor. And we apply that same logic. So we again have an original predictor, and we are trying to see what linear relationship exists between the original predictor and those partial predictions we made when we varied that specific predictor. And then if we subtract those partial predictions, we are left with that nonlinear effect that this predictor has on the predictions, right? And exactly the same intuition, we just have nonlinear effects instead of linear effects as we had them over here. Okay, and then our last effect is called the pairwise interaction effect. And what I'll do is I'll show you when it comes to the partial dependency function, right, which is this one over here, and over here, how we can calculate this joint partial prediction. So what we did before was we calculated the partial predictions, right, for each of our predictors separately. So this is what we see over here. But now I'm going to show you how you can calculate that joint partial prediction. In other words, a joint marginal effect that, for example, turbulence and the spot rate have together on your currency market rate. So if we can go back to our partial dependence function, we can see here that we will apply exactly the same logic, but instead we will vary, for example, turbulence and the spot rate together, right, according to a specific technique. And we will keep all other predictors fixed. So instead of isolating one specific predictor to obtain that marginal impact, we will isolate two predictors and vary them together according to the same technique, and then we will obtain that joint partial prediction, so a joint marginal impact of two variables together. So same logic, just with more than one predictor. And again, we can see that we're calculating that deviation, right? And then we're taking the absolute values of that deviation. And this time we divide by n squared. So we don't take the average, and then we get that pairwise interaction effect. And essentially all we're saying is if that marginal impact of these predictors separately, right, is exactly the same as the impact that the variables had together, then there is no pairwise interaction effect. Whereas if there is a deviation, so either their effect together, right, is greater than the effect that they had separately, then you'll have a pairwise interaction effect, and same with the other way around. And we can see again, if we look at this curve over here, now instead of having one predictor, we have two, so predictor 1 and predictor 2. We have that marginal impact, and then we have the response, right, which is just our pairwise interaction effect, which can be positive, right, and it can also be negative. We take the absolute value of that, and then we calculate that pairwise interaction effect. Okay, and then we can finally get to the decomposition of performance. So now that we know how to calculate these effects, now we can actually see how to use this model fingerprints across different models. We're going to look at that currency investment example. So we'll see that we have many different predictors that we want to use to calculate that currency rate. We want to make forecasts 1 month forward. And we'll see that not all of these predictors have nonlinear, linear, and pairwise interaction effects, but some of them do. So we can see that we have the currency turbulence, we have the equity rate differential, we have interest rate differential, the spot return, and the valuation, as we saw before in our toy example. And we can see that this is true, right, for the random forest, the gradient boosting machine, and the neural network. So this really helps us to compare different models. And as you can see, the gradient boosting machine and the neural net, already they pick up stronger effects, right, for all three. So for the linear effect, the nonlinear effect, and the pairwise interaction effect. So this is very interesting to note. And let's break it down into the linear effect across our three models, the nonlinear and the pairwise interaction effects. So for the linear effects, we see that the interest rate differential, valuation, and then the equity rate differential have that nonlinear effect identified by the random forest, and we see the same type of pattern, right? So relatively for the neural network and the gradient boosting machine, again, valuation, interest rate differential, equity differential, and the same for the neural net. If we look at the nonlinear effects, we can see that the interest rate differential again has a strong nonlinear effect. So this variable already is quite influential on our currency rate predictions. And we can see that again, the interest rate differential together with currency turbulence have a pairwise interaction effect on our predictions. So this gradient boosting machine and the neural network pick up on stronger effects than, for example, the random forest. This is also something to note. And what makes this very useful is not only to decompose performance, but also if you, for example, you have an ensemble method that you're applying and you're comparing many different models that you want to add, then you will not add a model with the same type of model fingerprint summary as another, because then adding that model would be redundant. So two models that have the same type of strengths, right, that are identified for linear, nonlinear, and pairwise, then you can remove one of those models, for example. So that's also very useful. If we can take a look at the heat maps quickly. So I just want to show you that it's very interesting that pairwise interaction effect we saw between currency turbulence and the interest rate differential has the same type of inverse relationship identified by the random forest, the gradient boosting machine, and the neural network. So in each diagonal, we have that same type of pattern, which is very interesting. And I just stated that this might not always be the case. So in this case, for example, if you have a high turbulence, let's say a low turbulence, then your interest rate differential and your turbulence will move together. Whereas if that turbulence increases to a certain rate, then they will have an inverse relationship. So it's very important to, and in this case, we are in the finance industry, so we need to find a reason, right, in the markets why this is true. And if this relationship was not present, right, in your random forest, your neural network, and your gradient boosting machine, so if they gave different results, then you would have had to go and identify why this is so in the specific industry that you're solving the problem in. So just take note of that. And then the last thing that I just want to look at is the performance on the training sample. And here we can already see that we have our neural network, our gradient boosting machine, and our random forest. So here are each of the results, right? And now we can finally compare them. And this paper also includes a linear model that we can compare to, and then also equity differential valuation, trend and carry. And again, this is just your, and I said it over here as well, your traditional type of strategies, just so that we can really make sense of what's happening to our models. And as I said here, if we look at the risk adjusted return, so this ratio over here, we can see that using machine learning models is very important, right? So they do give very accurate results, and we can see that for specifically the gradient boosting machine, the rate of return is quite high. Same for the random forest and the neural network, and our traditional models and also the linear model was outperformed by these models over here. So machine learning models are very useful, but we need to know how to interpret them. So we can also see that the kurtosis, right, for the specific return for the gradient boosting machine, so even though it's quite high, the kurtosis is also quite high compared to other models. And this just means that there will be great fluctuations in this return. So we just need to take that into account as well. And then the last thing I just want to highlight is if we look at the cumulative return, right, we can see that over time, the neural network, so this red curve over here, and the blue curve, and then the gradient boosting machine, which is the red curve, they follow each other closely and they outperform the random forest, which is this gray line over here. Also carry, trend, valuation, and the equity differential, and then also the linear model. So now we can use the model fingerprint to actually figure out why. And if we go back to our summary, we can see that both the gradient boosting machine and the neural network picked up on those effects, right? The linear, the nonlinear, and the pairwise effect, whereas the random forest did not pick up, as strong, all of these effects. It did not identify them as the gradient boosting machine and the neural network. So this just gives us an insight into why these two models are performing well, and why the random forest is not performing as well. So this is the basic overview of how we can use the model Fingerprint, why it's unique, and what makes it great. And then I just want to thank all of you for joining the session, and see you next time.